Hello, everybody. It's my pleasure for me today to introduce our speaker, Quoc Tran-Dinh. He is now an associate professor at the Department of Statistics and Operation Research at the University of North Carolina at Chapel Hill. Previously, he was a postdoc at the École Polytechnique Fédérale de Lausanne in Switzerland, and he got his PhD in optimization in engineering at KU Leuven in Belgium. Quoc, it's your state now.
All right, thanks for the introduction, Ming. I also want to thank the organizers for making this seminar series and give me an opportunity to talk at this seminar. So my talk today is basically on a joint work with my PhD students, Nhan Pham, and two colleagues from IBM Research. So it will be on the topic of Douglas-Rachford splitting algorithms for non-convex composite optimization problems in the context of federated learning. So let me, the talks is based on the paper that we posted on archive here. However, we need to update a little bit because it's some of the minor changes in the paper. And my talk will be divided into three main sections here. Let me start with the problem statement, a little bit of motivation and what we got from the this work, and I will present two algorithms. The first one is on the randomized Douglas-Rachford, and the second one is basically one variant of the first one is called asynchronous Douglas-Rachford schemes. Then I might show a few numerical examples on some of the algorithms that we have here, and I close my talk with some conclusions and some future research ideas. So the problem we are interested in is the following optimization models. By the way, if you have any question or comment, please interrupt me at any time during the talk. Thank you. So the models that we are interested in here is to minimize the sum of Fi. So basically the average of Fi plus the regularizers Z. So the function Fi are assumed to be smooth and possibly non-convex, but the function Z is convex and possibly non-smooth, so the opposite. And we define the function F as a sum or average of Fi. So the goal is try to develop the algorithms to find a stationary point of this problem, because the problem is non-convex. So our hope is just trying to find first order of stationary point of this problem. However, in order to develop the algorithms, we need a set of assumptions. So let me state them here. So the first three are, first four assumptions here are basically to make the problem well defined. So like the smooth of the function F and the convexity of the function Z. The domain is not empty and the stationary point exists, and the function bounded from below. Only one assumption that I want to highlight here is the Lipschitz continuous of the gradients. It's called the L smooth. So the function Fi has a Lipschitz gradient. That's the main assumption that we need for developing the algorithms. All right. So because we want to consider this problem in the context of federated learning, one of the recent topics in machine learning where people try to solve large-scale problem in the network. So that's why I just want to recall the concept of federated learning taken from Wikipedia. I hope it's some sort of like short definition. So basically, it's a machine learning techniques in order to train an algorithms across multiple decentralized devices or users. Here, the local devices or users hold the data, sample data locally, and they are not exchange them. Basically, it's due to the private concerns. So they hold the data in their local in the local users, and just exchange some information, but not the models or the data, or maybe the gradient of the function or something like this. So because of that requirements, they create a sort of challenges for this kind of learning problems. So there are 4 main challenges here. The first one is communication bottlenecks. So basically, because the number of users could be large, it's of course creates communication bottlenecks, right? Because we need to exchange the information between users, and those users could be different as well. Then therefore the network also could be is not homogeneous. The second challenge on this data. So it's the data heterogeneity of the data, which basically they may have a different distributions in and also different size of the data sets in the local user. The third one is on the system, because system is in general is not homogeneous. So they could be very different, or I mean the user could be different from one to the others. And of course, the network could also be different in terms of connectivity, or the powers, and so on. So that also creates a lot of uncertainty or you know, unstable connection and so on during the training process. And the last one is related to the privacy concerns, which is basically the data here need to be stored at the local user or agents without sharing them, and yeah, we can only query some sort of information from the user. So because of those challenges, this requires some sort of rethinking in the developing the algorithms for this kind of models. So our goals in this works, we try to handle some sort of challenges we identify above in order to solve the model, the problem on. Here we developed 2 algorithms based on the Douglas-Rachford techniques. We combine these techniques together with the randomized block coordinate strategy and some other techniques like the asynchronous implementations in order to handle those challenges. And in terms of the contribution of the works, we have 2 different algorithms, but the second one can be considered as a variant of the first one. So the first one is very simple ideas. We combine this classical Douglas-Rachford splitting techniques together with the randomized block coordinate strategy to handle those problems. So the goal is try to use only a subset of user for each communication round, so that we don't need to go over all the users for each round or each iterations. So that helps to reduce the communication bottlenecks. And here we try to also solve the problem at the user inexactly in order to make it more realistic, because we are not be able to compute the exact solution when the function is complicated. Eventually, we can show some sort of complexity for the communication of the algorithms. So that is our main contribution. Look back at the literatures, we can see there are so many works around this topic. So I just try to show some of them which are most related to what we're doing. The first algorithm, probably fast average, basically is some sort of like averaging algorithms combining with the SZD. So so that algorithm it requires a set of assumption which is stronger than what we did in order to guarantee the convergence. So the one of the early steps to show the conversion of the fast average is due to Stick 2018, which is a few years ago. The second algorithm is called FastFrog. Is kind of an extension of FastFrog, fast average, which is in order to deal with the heterogeneity in the federated networks by introducing the proximal term, and basically in order to handle like some sort of like connection between variables in the problems. Other algorithm like scaffolds or month, I don't know how to pronounce it. MIME, and the other two, which is more related to our work, is fast split. Basically, also relies on similar ideas. It's on the Fishman-Rexford scheme, which is a variant of the Douglas-Rachford, and it's only consider the convex problems, and I will show the difference between this and our work. And the last one is GoFast PD, is the Freiman-Dual algorithms. Basically relies on the augmented Lagrange function methods for the nonlinear optimization problem. So basically, they reformulate the problem into the constraint problem and then handle the constraints by the augmented Lagrange functions. So that is some related works that is, I think, mostly related to our paper here. However, there are so many other algorithms that we are not able to list them all. So because we handle the constraint problems, the composite problems, so therefore we use the proximal operators for both function fi and z. Of course, fi is smooth, we can actually use the gradients. However, in this work, we are trying to use a proximal operator of the functions. Even though fi is non-convex, but the proximal operator remains well defined because of the Lipschitz or the L smoothness property. So, and then for function z, because it's convex and non-smooth, we want to use the proximal operator of the function z. So then, therefore, we recall the proximal operator here. And then we define the gradient mapping is basically some sort of the mapping to characterize the optimality conditions. So whenever a point x star is a stationary point of the problems, then the gradient mapping at that point will be 0, right? So the goal is trying to approximate this point. Then we approximate it in terms of the norm of the gradient mapping to be small in terms of the expectations. The expectation is taken over all the random maps that we generated by the algorithms. All right. So I think most of people are familiar with the Douglas-Rachford algorithm, but so I just skip this step. What I want to say here is when we solve the problem this form by Douglas-Rachford scheme, we can reformulate the problem in terms of the stationary point in terms of the fixed point formulation. So if we define a map like this, mapping like this, go Douglas-Rachford mapping, then actually the Douglas-Rachford scheme can be written as a fixed point iterations in Y. And then in order to compute the solution, we need to do one more step like this. So that is the way that we can bring the Douglas-Rachford into the fixed points. Why I want to do this? Because later on, actually, we want to, if we want to apply the coordinate descent on the fixed point formulation, we'll see some difference between classical coordinate descent and coordinate block coordinate methods and this new scheme. All right. Any question or comment? All right. So all right. So let me move to the first algorithm and to see how we develop it. So first we reformulate the models, the composite model at the beginning, into a constraint problem. So this technique is usually do in this setting, in this kind of problem. So what we do here, we try to duplicate the variables in order to break the finite sum into a decomposition form, so that each function now is depend on an independent variable xi, so that we can use the proximal operator of each function, right? So of course, by doing that, we need to impose constraints in order to make all the variables to be the same. So if we do that, then the problem is significantly large, because the variable now is concatenates of the n vectors, and it will be in the Rn times p. And we define this as a subspace because it represents a subspace in R and P. So by doing this, we can bring the problem one into this constraint form. However, in order to apply the Douglas-Rachford scheme, we remove or we handle this constraint by using its indicator function in order to make it as an unconstrained problem. So we just simply remove the constraint and put it into the indicator functions. So the problem now is just simply the sum of three functions. So we can easily show that if x star is stationary point of the problem 6, then one component x1 here could be the stationary point of the problem 1, and vice versa. So therefore, solving this problem, and we can also solve the problem 1 and vice versa. Okay. So the first step is very simple and very classical. People always do this. Now we apply the Douglas-Rachford scheme to solve the problem number 6. Then of course we can draw in this form, right? So the difference here, we add n times the parameter step size eta. So this is in order to just scale it a little bit. And we add relaxation parameters here between 0 and 2. So if it equal to 2, then it go back to the Fishman's Douglas schemes. So this step is nothing new. So now we want to express all the steps here in a more concrete or implementations. So first step is just simply nothing, just a vector. So we do it blockwise or concatenate them together. However, step 2, we want to focus on step 2, where we can use a decomposition structures in the function f to compute xi k for all the I from 1 to n. So by doing this, we can decompose the proximal operator of the function f, the big F, f of big X, sorry, into each component, right? So that step is also simple. And then we introduce a intermediate variable x hat by adding this, and then we compute the proximal operator of z plus delta L. So this is basically basically can be computed in the closed forms. So basically what we need to do is we need to solve this problem, right? This constraint problems. However, because it's on the subspace, so therefore we can use dual methods to solve it explicitly. By using the Lagrange function and so on, we can solve this problem explicitly. So after doing those steps, we obtain the implementations variance, which looks like this. So here there are 3 steps here can be implemented in parallels for I from 1 to n. And then the last step is basically we can write into 2 different separate steps here to show that this step is actually nothing but just the averaging step. And the last one basically takes the props of the averaging step. So the point here is how can we randomize 3 steps together? So keep in mind that the problem we are handling is non-convex. Although the Douglas-Rachford schemes initially developed for the convex problem, or more general is the monotone, maximum monotone inclusions. Here we use this for non-convex problem. Of course, the people already studied the non-convex problem as well, and the algorithm basically is the same. The difference here, we try to randomize the subset of users from n in order to use only part of the updates here. So by doing that, we need to sample the same subset for all 3 steps here together. So therefore, it is kind of like different from standards, standard coordinate descent methods I will show later. Then we keep the others out of the set, we keep them unchanged, so that the algorithm that we will get after randomized, applying randomized block coordinates updates. So one of the challenges here is basically to analyze the conversion of these methods, because we sample 3 steps at once, so they are sequentially. These steps is actually implemented sequentially, but at the same time we sample it. So this is leads to some sort of challenging in analysis, because it not follow exactly the classical block coordinate descent coordinate methods. So a second point is it seems that we don't know exactly, but we cannot switch the prop of f and g. So in the convex case, if the function f and g are convex, we can exchange f and g step, right? Because the roles of both functions is the same. However, in this case, f is non-convex and z is convex. So when we change it, we need, basically, if we want to exchange the 2-step or switch 2-step, we need to shift the index of the iteration. Then this also brings some sort of difficulty in the analysis, and we don't know how to do it. So come back to the coordinate method. Basically, if we apply the coordinates, block coordinates methods to the fixed point iteration, so this will be the typically the algorithm, right? So basically, we only update one block at one time, and then keep the others unchecked. So that if we this algorithm, like the one of the example here is for ROPS, it basically relies on this update. Of course, they also do asynchronous versions, but the essential idea is this one. So many methods can be written as a fixed points, and then the same for Douglas-Rachford. And then we can apply the classical block coordinate methods to that fixed point formulation, and we get the algorithms. However, for the Douglas-Rachford, it's quite different because the iteration here is in Y, something in intermediate stage, it not the output of the algorithm, right? So that also create a difficulty when we apply the coordinate descent, coordinate methods. And at the same time, if we apply poorly these methods to these operators, we still need to compute the full proximal operator here, right? Because this is inside instead of outside. For this, we can use a block, but this is not, because it's inside the function, inside the operators, right? So that also create a difference between this and trading or classical coordinates and coordinate methods. All right. So so our algorithms here, after doing the randomized sampling step, we basically get this algorithms. So in order to present it in terms of the Federated Learning, basically what we do here, we initialize every point, every vectors here on both the server and the users. And then at each user here, we select a subset of user, which is called active users. And what we do next is we just operate on that subset. So each user on this active user here receive a vector X bar from the server, some sort of information which now using the data here, right? And then each user start updating their iterates based on these 3 steps. After having the information, this will send back to the server only this information. They don't send the data, they just send the increments where the updates. And then the server, it aggregates in order to compute this, and then they apply the procs and then send it back. And that is the algorithm for this kind of learning. So this called randomized or Douglas-Rachford. So here we also allow them to approximate. We also allow this sampling scheme to be a little bit more general. It's not necessary to be uniform. So we only require that for every subset here, the probability of the updating each user must be positive. So by imposing this condition, we can show the following results. We can show that with the given parameters. So here I only state this for this exact case, meaning that the proximal operator is computed exactly. We also have a result for the inexact case, but it's a bit more complicated, so I just leave it out of the presentation. So here the step size. Keep in mind that because alpha between 0 and 1 and 2, it doesn't cover the Fishman-Rachford methods. So that is different from the first split, the algorithm that I mentioned earlier. So by using the step size and all parameters, we can show that the right-hand side here is essentially the average of the gradient square. Gradient mapping square will be converged with the rates of 1 over k. And of course, the constant c here depends on all the parameters that we have, including the Lipschitz constant, step size, and the probability, and also relaxation parameter alpha. Of course, we're not trying to optimize this right-hand side, but that could be done. When we take the output as uniformly at random from all the x bar k, then we get the complexity of the commutations. So as usual, it will be 1 over epsilon square, where epsilon is the accuracy that we want to achieve. So this result is usually the case in a non-convex setting. Not sure if there's any question or comment. All right. So let me move to second algorithm. So second algorithm is basically motivated by the system heterogeneity. Because as I said at the beginning, the system may have a different power, networks, connectivity, and so on. This requires the, to handle it in a different ways, because in the algorithm that we have, the algorithm here, it may need to wait. So one user need to wait for others to complete, right? For all the other user on SK to complete the computation before doing the aggregation. So in order to avoid that, we want to develop, say, some sort of asynchronous variance, which is trying to solve that problems. So that is what it means. It basically at each iteration k, the user will receive a delay copy. It's not exactly the vector x bar, but some delay copy of that one, because whenever one active user is updated, then it sends the information to the server, and server start aggregates the model, and then just broadcast again x bar. And some other user, maybe they are still reading from the server. So therefore, what they read is not exactly the new update, but some sort of delay copy. So that it's different from this algorithm and the first one. So in the analysis, we count the iteration by whenever one user completed its update. So then we count for one iteration, while the others might be reading. So that is only different, and the algorithm is almost the same, except for now we have a delay vector d, represent for the delay for each users here. So this is not the scalar, but d is a vector for each user. And for the active user, it's receive a delay copy and start updating. So only this step is different, and others remains the same, right? However, the analysis of this variant is much more challenging than the first one, due to the case that we need to handle the delays. We adopt some sort of recent models. It's called probabilistic models from some recent works, in order to allow that the index or the active users and the delay vector could be dependent. So they are not necessary to be independent. So that's a new models allows us to handle a little bit more broad class of architectures in the asynchronous system. So one of the assumptions that we require here is the probability of updating each user in a certain number of iterations should be positive. So meaning if we fix the number of iterations up to t, then in that range, the probability of updating from each user here must be positive. And of course, the delay vector should be bounded as well. So we will not handle the case when the delay is unbounded. There are some works they handle the case when delay is unbounded, but decreasing probably exponentially. So in this case, we have some technical parameters, which shows something quite interesting. The first parameter is related to something. Delay here is basically satisfying some condition in terms of the number of user. So when the number the t tau, the delay is less than some sort of square root of n, then we can choose step size a little bit larger. However, when this not satisfied, then our step size becomes smaller. Then we define some formulas to compute some of the quantities here, but that's only the point I just want to mention. And after setting the parameters as in this slide, we obtain similar results, except for that the constant now is different. Is not the same. So this constant is different. It depends on all the parameters related to this algorithm, including the number of iteration t here and the delays and also the probability lower bound. And we get this quite similar results except for that one. Okay, so I think let me check. So that's the two algorithms that we have, and let me show a few numerical examples that we my students implement and test on some of the algorithms. So we try to compare the algorithm here together with the other methods like fast average, fast prop, and fast PD. And we use both synthetic and real data, and we use a neural network to compare these algorithms. So so my student tried to implement the algorithm using the previous codes downloaded from others, and he implement on top of it. And we run it on the cluster, Linux cluster, because this is quite heavy computation. So he generates different data sets using the techniques in this paper, basically, and then try to sample the randomly the user on a small subset. Of course, it's already known that for some of the problem like is not homogeneous data set, the algorithm like fast props or fast average, it usually underperforms compared to the one we can handle, you know, the heterogeneity property, right? So that's the first case when he tests that one. And also, we also compare with the fast PD. So the reason why it's slow because fast PD is only has full updates. Therefore, when we count the number of communication round, it's basically it will be count within how many users use for each round. So that it also leads to some sort of slower in the fast PD. So yeah, so there are some sort of like observation here, as you can see. For the other method, we call the non-homogeneous data sets. Here we use a set of 50 users among 200, and of course this also affects the performance as well. The larger is usually better, but it's also slow down the conversion or the communication routes, and so that we can observe some sort of observation due to the heterogeneity of the data. And this is on the real data set called MNIST data set, which is extension version for the MNIST data set. All right, so we also try to, so the previous two examples without regularizer. If we use the regularizer, we can see some sort of different, because the effect of the learning rate on the performance here. So the learning rate here basically represents the accuracy in computing the proximal operator of the function f. So what we're trying to test here is we try to test if we only update a few iterations, then what happens? Or if otherwise we increase the number of iterations in computing the proximal operators. So by doing that, we can actually show, of course, more accurate is better, but it's a slow down the algorithm as well, right? So if we use 5 epochs, then of course it's performed like this. When we increase it, and it perform better, but we don't count the time here, because here it's only show the effects of the accuracy. Yeah. So we also try to compare this with the asynchronous, because implementing the asynchronous one is more challenging. So we only take our full not asynchronous and compare with the asynchronous one on this data set. It's very hard to compare exactly. So what my student trying to compare is in terms of their times. So, but of course, other factor may also affect the performance. So that is the first some of the preliminary results I just want to show here. So let me close my talk by making some conclusions here. So we basically developed two algorithms, and based on the idea of the randomized loose-lag force for the non-convex problems. Of course, the algorithm has some sort of theoretical advantages, including the use of the subset of user per round, per communication round, and it allows the asynchronous implementations, inexact computation, and can handle the composite form. The results that we got here in terms of the complexity is mostly the best known result that we have seen in the literature under standard assumptions. And with some numerical example, we can see some of sort of like promising performance, even though we are not test the algorithm with the intensively. So for the future research direction, we are trying to work on the convex setting. The idea is trying to accelerate the loose-lag force algorithms in the convex setting. And we try to also to incorporate the second information as well, or trying to incorporate the compressions ideas, and also adaptive variance, and so on and so forth. So that's all I wanted to say today. Thanks everyone for your attention.
Thank you, Quoc, for the nice talk. Now it's time for the discussion. If anyone have question or comment for Quoc, please unmute yourself and ask your question, please.
No. Yeah. I have a question.
Yes,
Okay.
yes,
Sure.
yes. Mark?
Thanks for your talk, Quoc. So correct me if I'm wrong, but you assumed that the finite sum function was differentiable and the gradient was Lipschitz continuous, right?
Yes.
Whereas
yes,
the other
right.
one was non-smooth.
Right. Yes.
But on the other hand, the Douglas-Rachford algorithm, you compute the prox, so you don't use the smoothness of the function directly. So what's the motivation for using, say, Douglas-Rachford here rather than trying to adapt like a projected gradient or a forward-backward type method where you can just evaluate the differentiable function or the gradient of the differentiable function?
Yeah. Thanks for the very tough question, I would say. Actually, when the function is elliptic and smooth, you can actually use the backward forwards, right? It's scheme, and you can show similar results. Well, we want to try this, and we don't know. We hope it because there are so many works in this direction where people use the Douglas-Rachford for non-convex problem. The assumption remains the same. I think they have some sort of maybe, or I don't know exactly if they perform better in terms of like is it usually in the splitting or in the operator splitting ideas might be performed better than the using the gradients. So in terms of the conversion guarantee, I haven't not checked if the factor in front of the conversion complexity bounds could be better or not. This is, I haven't not checked it yet, because our formation looks quite complicated to optimize. So but maybe we should check that. Thanks for the questions.
Okay, thanks.
I have a question. So I think in the normal formulation of Douglas-Rachford is for, say, for the sum of two functions. Normally in the non-convex setting, normally people assume one function is differentiable as in your assumption to obtain the global conversion. To obtain the global conversion of the main sequence. So do you have the conversion for the sequence, say X bar or Y or something?
Yeah, good question. I think this thanks. Yeah, we only look at the the norm of the gradient square. I think is one step we should consider as look at the subsequence of the or entire sequence. I don't know, it's an entire sequence. It could converge to the stationary point or not, but I think maybe we can be able to show the subsequence. Yeah, I guess I haven't tried this, to be honest.
Okay, thank you. Any question or comment? Any other question or comment?
Yes, Quoc,
Hello.
thanks for the talk. You mentioned you've got a lower bound, an upper bound, or best known upper bound on the communication complexity.
Right.
Is there any non-trivial lower bound on this communication complexity?
Yeah, it's a good question. I think for some of the algorithms, they have a lower bound, but for this particular algorithm, I have not seen it yet. I have not tried to follow that direction. I think it's very interesting to look at the low bound for the Douglas-Rachford, but I think for some of the other algorithms, they already have a lower bound.
There's no lower bound that's sort of independent of algorithm, is there?
Yes, so to be honest, I don't really know if it's easy to find this. Maybe through example or I haven't tried that. But thanks for the question.
Thanks.
Okay. We still have time for questions. So if anyone have questions, please.
I just want to mention, so for the convex or the monotone operators, the works from the Combat and POSK are, it's already developed the randomized variant for this kind of algorithms in 2015, I think. They developed for general monotone operators, but the techniques there, we cannot use it here because the problem here is non-convex, or at least we don't know how to use it. And the proof techniques theirs based on the sequence, the norm of the sequence of the iterates. So here we basically use another techniques, relies on the sum-Lyapunov functions.
Yes, right. Yeah, of course in the non-convex setting, is the situation is difficult.
It different too. Not sure if it much more difficult or easier, but I think they use different techniques.
Yes. Normally I think in the convex setting they can formulate formulate back to the formulation of the sum of two functions or two monotone operators, and then use the average net for to get the conversion.
Right, yeah.
Okay, if there is no question, so please join me to thank the speaker again. Thank you so much for joining us today.
All right, thanks everyone for joining me today. I'm really happy to see a lot of names, very family names that I've seen on the papers and books, but I haven't not met. You are, hopefully there's conference and we can meet somewhere like Matthew or Alex and so on. But thanks a lot for joining me.
Okay, thank you.
Thank you very much, Quoc.